Okay, welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. So no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. So that's about it. Let me actually get into the exciting parts. Introducing our today's speaker. Today, it is an honor to host Jiansun Wang, who is the Robert Uder Collegiate Associate Professor of Aerospace Engineering in the Department of Aerospace and Mechanical Engineering at the University of Notre Dame. He earned his PhD in aerospace engineering from Virginia Tech in 2017 and worked as a postdoctoral scholar at UC Berkeley before joining Notre Dame in 2018. Dr. Wang has a multidisciplinary research background that spans scientific machine learning, data assimilations, Bayesian computing, uncertainty quantification, and computational fluid dynamics. His research focuses particularly on the in-depth integration of the advanced AI ML techniques with physics-based mathematical models and classic numerical methods, aiming to revolutionize the field of computational modeling in the era of big data and significantly enhance the predictive simulation capability. He has led research projects sponsored by multiple agencies, including NSF, ONR, AFSOR, DARPA, and Google, and others. Dr. Wang is a recipient of the 2021 NSF Career Award and 2023 ONR YIP Award. He is also an elected vice chair of the U.S. Association for Computational Mechanics Technical Thrust Area on Data-Driven Modeling. Today, Dr. Jiansun Wang will talk about Neural Differentiable Physics, Unifying Numerical PDEs, and Deep Learning for Data-Augmented Computational Physics. I'm sure we are going to hear a wonderful talk. Now let me, before I pass the baton to him, let me ask him a question so that we know, something about Dr. Wang. So my question today is for you, Dr. Wang, is I happen to know you're very interested in sketching, but for now you cannot do that because you're so busy, doing writing or all stuff and on the computational mechanics and data-driven modeling. If you can briefly summarize how you got, where you are right now from enormous interest in the sketching. That would be awesome.
All right, thank you, Yunsu, for this very kind introduction. So your question was like, how am I gonna? So I'm not sure I understand your question.
How your journey of pursuing the sketch to where you are right now? Yeah, if you can briefly describe that.
Yeah. So I learned like painting, drawing, and in my childhood. So actually, I learned that for almost more than 10 years, and that's kind of I like to drawing things when I was a child, and that's kind of lead my so as I mentioned to you, like when I started to choose my major and undergrad for the undergrad majors, and I try to study like the architecture because I think that's going to leverage my kind of this interest in sketching and drawing, and eventually I got admitted to like naval architecture and ocean engineering. So that's completely different, even though they have like architecture. So and that's how I started to learn the fluid mechanics and solid mechanics, and I start kind of learn the fluid computational mechanics, and that is, I feel like, how this my hobby in sketching and lead me to a scientist in computational mechanics in general. And I spent like the past 10 or 20 years learning and working on this area. So yeah, I think I'm still like doing sketching in my spare time. But you know, that this is what I'm kind of like what I'm like doing the computation and coding. But yeah, thank you.
That's very interesting life path that you have taken so far. Well, thank you so much for sharing your story. The floor is yours now.
Okay, all right, thank you. Yeah, thank you. So good afternoon or good morning, depending on where you are. So I know like a lot of people from the East Coast or West Coast. I would first like to thank Yongsu for giving me this opportunity to present my work. I am very excited about this opportunity to share with you guys our research on scientific ML and AI for science. As we know, like AI has been very successful in the past decades, especially in the area of computer vision and natural language processing. I believe many of you have been using large language models like ChatGPT daily. And if you have a Tesla, you probably have already tried their full self-driving capability, which is kind of cool. I didn't purchase it, but I've tried it when they have like free trial. So those are like highly rely on the AI-enabled computer vision. Well, in our group, we are interested in how can we leverage the success, use AI and data to address the scientific challenges, and particularly to advance the computational science by developing the next generation data-augmented AI-empowered computational modeling and the simulation capabilities. So in this talk, I'm going to show you some of our recent works in this direction. Especially, I would like to introduce this Neural Differentiable Physics, which is a framework to unify the numerical PDEs and deep learning, and for data-augmented computation modeling for complex system, complex the spatial, temporal physical phenomena. All right, as we know, the computer-based modeling and simulation capabilities plays a central role for us to understand, predict, and control complex systems like turbulent flows, flow structure interaction, the thermal fluid couplings, and complex multi-physics phenomena during the advanced manufacturing processes. All of this physical system often exhibit this complex spatial temporal behaviors, and which generally can be described by a set of partial differential equations, which are known as governing PDEs, right? So simulating or predicting this physical process is basically to obtain the solution of this PDE system, and by giving the specified initial and boundary conditions. Well, this has to be achieved numerically, where the PD are discretized into a big set of algebraic equations on the discretized domain using like the numerical discretization methods such as finite difference, finite volume, or finite element. Well, depending on different numerical method, programming languages, or problem of interest, there are many different implementations known as those numerical solvers, which are either open source or commercial, such as ANSYS, OpenFOAM, Phoenix, Abacus. Well, essentially, this is like from the traditional perspective to talk about the computational modeling. And this paradigm has been very successful for the past several decades, and people have used the physics-based numerical solver to study the physics and make the prediction in many applications. However, they also face some challenges in many practical scenarios. Like if we consider a very complex systems, so usually a complete and reliable governing equation may not be fully available. This is because either like the underlying physics are too complicated, which has not been fully understood, or it is because simply like it is infeasible to resolve all the physics. For example, like we know we know like even the most complicated turbulence flows can be exactly described by Navier-Stokes equations. However, it's not feasible to resolve all the turbulence scale down to the common growth scales for any flows with arbitrarily high Reynolds numbers. So we have to model those fluctuations or small scales using the SGS closures. But what is the true model form of the closures, and what is like the true constitutive relations? Those are not known, right? And secondly, the input to the models are often uncertain or even unknown, and making this forward simulation result not reliable. Here, what I mean by input are like the initial boundary conditions, geometries, those physical parameters, model coefficient. So for instance, if we try to simulate like a patient-specific cardiovascular flows, how do we define the inflow boundary condition for a different patient, and how and also like the material property of the vessel wall could vary from patient to patient. And we cannot easily like do the mechanical testing for each individual patient by taking their vessel out, right? So for those in vivo patient-specific simulation, many input parameters are not known, making the forward simulation, unreliable. And another very well-known issue of this conventional numerical solver is the computational cost. So basically for most non-trivial scenarios, this simulation could be computationally very expensive and make them not feasible for real-time or many query applications. For example, if we want to finally achieve digital twin, and we need the real-time predictions, and that is able to assimilate data in the real time. So in many applications, such as solving like inverse problem, optimization, or quantifying uncertainty, we really need to repeatedly run the forward simulation for so many times. So if a single simulation can take days or weeks, conducting those manual inquiry, applications would be impossible. Well, luckily, we are in the area of like big data, where the high resolution heterogeneous data has been like generated daily from either experiments, high fidelity simulation, or field observations. And also thanks to the rapid development of like the experimental and simulation techniques. And we also see like there's a rapid development of the GPU hardwares and GPU computing, and not mentioning the recent advances in AI and machine learning. So basically, all of this motivate us to explore maybe like data-driven solutions to address the challenges I discussed above. Actually, in the past few years, there has been a growing trend of exploring the use of deep learning to accelerate the simulation or efficiently like emulate the spatial temporal physics in a data-driven manner. As a surrogate models. Some of the works show the promise to a certain extent. Usually, I use the SmashGraphNet as one of the examples. It's one of the example of this data-driven neural simulator for the spatial temporal physics, and this is developed by DeepMind about 2 years ago. As you can see, like from this animations, the same models can be trained to learn the variety of spatial temporal physics, including solid deformations, fluid structure interactions, simple aerodynamics, fluid dynamics, those periodic vortex sheddings. So the results are visually kind of impressive compared to like the high fidelity, like numerical reference. However, their model structure is quite simple, which is nothing but a message passing graph neural network to capture the dynamic transition of the state from the current step to the next step, which is trained in a data-driven way. So conceptually, this is simply to train a black box neural network to learn the transition from UT to UT plus 1. Use tons of labels of this T to T plus 1 pairs, right? So once trained and given an initial condition, the model can autoregressively, roll out and predict the dynamics. And this autoregressive model evaluation, we call it model rollout. So this type of model is the simplest, pure data-driven next step neural predictor or you can call it like a neural operator because you're learning those operator defined from T to T plus 1. So we actually work with DeepMind, like the Toby as the first author of this mesh graph net to test the model on a few simple fluid dynamics problems. So here I'm showing like the cylinder flows, which has the periodic vortex shedding. As you can see that the mesh graph net predictions after a long-term rollout still looks very physical. However, compared to CFD reference, the phase is actually completely opposite. So if you check the history of the drag coefficient, where the green line is the mesh graph net and blue one is the reference, well, the prediction capture, the overall like behavior, so from a transition stage to the periodic vortex shedding stage, there's a clear phase shift can be seen. And this is actually a very simple case since eventually dynamics become periodic, which is not so hard to capture in a data-driven manner, right? So if we move to a slightly like more challenging scenarios where we consider a channel and we put a jet at the inlet, so the angle of jet can change over time. So it'll create a slightly more complicated vortex dynamics. As you can see at the beginning, the data-driven like neural simulator can capture the dynamics reasonably well, but quickly they becomes noisy and eventually not physical at all. Well, we know this is due to the issue of this next step autoregressive models, since the error will be accumulated during this model rollout. So we always see the poor robustness of these models for long-term model rollout, especially when the dynamics become more chaotic and turbulent, right? Another issue for this purely data-driven model is the generalizability in out of training regimes. So when testing the model on completely different, like new initial condition, boundary condition, new parameters like Reynolds numbers, which are far from your training range, and the prediction could go wrong easily. So the question is how to improve. You may say that, okay, the current next step model formulation seems quite simple, and definitely this can be improved with more advanced sequence model, like using the memories like the LSTM or incorporate like temporal tensions and make it more like a transformer like a model. We have done that and improved the mesh graph net using like the temporal like transformers and graph encoding, and it did improve the result. For example, if you see the orange line here in those figures, they actually have a better agreement with the reference. But still, the main issue of this poor robustness and generalizability, there still exist. I don't think by simply like changing the neural architectures would completely solve the issue of data-driven models. So let's think about what we did so far. So up here, we completely like rely on data, and everything essentially is a black box, right? Well, so however, we're not completely blind to the system we try to model. So we usually have some prior knowledge about the underlying physics. Namely, we know the governing physics represented by the PDEs to a certain extent. Although, as I mentioned before, the governing PDEs may not be, fully available, complete. So some portion is uncertain or unknown, such as some constitutive relation closure terms and some complex physical process that the mechanism behind it is not known. So we don't have a like a physical description of those couplings. Or sometimes we just cannot computationally resolve everything, and we have to we cannot basically resolve some part we cannot resolve. So this physical prior is kind of I call it kind of vague. Now the question is how can we leverage this incomplete and vague physics to enable a better data-driven modeling? So when people talk about like physics-informed learning, one popular way of using the physicalized, well, we can use that to regularize the model training process. Namely, we can penalize the violation of the physical law or constraints by incorporating the residual of the governing equations into the loss function, and which essentially just regulates the neural network training. And this is a general idea of physics-informed neural network, or PIN, right? A lot of work has been done in this directions, including our group. We have also contributed to this areas many years ago. However, no issue for PIN is the nonlinearity is introduced by the PDE loss. And also this multi-objective optimization. You have many terms in the loss and make the training more difficult. And in many complex scenarios that basically cannot be trained well to get converged solutions. And more importantly, as I mentioned here, we are talking about the scenario that the physics prior is kind of vague, namely that like the governing PDEs is only partial know. For example, we only roughly know, well, this process is diffusion dominant, and there's a lot of like unknown things. It's not possible to formulate like clear like this physics informed a lot, since the complete model form of the PD residual is not known. So in this talk, I would like to introduce a different idea of how can we integrate the physics into the data-driven like deep learning models. Instead of using the governing equation to regularize the neural network training in a soft manner like the PIN, we are trying to integrate the PD operators in the partial know governing equation as a part of the neural network architectures. Well, this is motivated by the foundational relationship between the neural network architectural component and numerical PDE operators, which has been recently actively explored in the deep learning community. What I mean by like neural architectural components are those like building blocks for deep learning architecture, such as the residual block, residual connections, convolutions, graph kernels, massive passing, attention mechanisms, recurrent structures, and so on, right? So this can be kind of linked back to the PD operators and their numerical representations, like those different numeric schemes. So here, let me give you some examples to make it more concrete. So in the architecture of the well-known RASNet, right? So this is a very famous like neural network architectures, which are constructed by many residual blocks. And in this residual blocks, the RAS connection is basic building blocks. Which was proposed to solve the vanishing gradient issues originally. So conceptually, the residual connections layer simply take like the current state, UT, right? And apply the transformation function with the neural network, like the trainable neural functions, and add the output back to the original state. And this process can be interpreted as a discrete approximation of ODE using the forward Euler scheme. So depending on the trained neural functions, and we can always find a corresponding continuous ODEs accordingly. So reversely, we can use this continuous ODE to define this residual connections, which essentially has infinite number of layers, or it has infinite depths. And this analogy between the residual connection and ODEs has inspired the creation of a new class of the RASNet architecture known as the neural ODEs, and which has been like kind of popular in the deep learning community as well in the past few years. Well, another example is like the mathematical foundation of convolution neural networks, so the convolution layers, right? So if you think about the spatial PD operators, such as like diffusions, and can be approximated using like a finite difference. See, let's see if we use central difference, or the stencil actually define a convolution kernel, right? And the PD operators can be interpreted as the convolution operators. And namely, the standard convolution operators can be linked to the finite difference-based spatial PD operators on a uniform grades. So any PD operators such as diffusion, convection, gradient, and can be expressed as convolution operations. And the convolution kernels reversely can be interpreted as one of the spatial differential terms and with certain discretization schemes. Well, this relation can be extended to like irregular domains or like non-Euclidean space by linking the graph convolution operators with, for example, finite volume-based spatial differentiations. And more examples include like the relationship between the recurrent network structures and with control differential equations and implicit schemes. And just to name a few. And if you think about the temporal tensions, and it can be interpreted with the like high order time steppings. So here, let's go back to our goal is we would like to build a sequence neural network such as conv-LSTM, for example, to learn the spatial temporal physics and rely on data. So we're still like trying to develop a data-driven model, okay? Like we want to build a conv-LSTM and to this sequence model and to learn the data and build this autoregressive model. So if we know the complete like form of the true governing equations, and we can choose to build this RN completely based on this PDEs, meaning like those convolution kernels, rest connections, and recurrent structures can be completely determined by the PDE operators with specified discretizations. And in this way, it's basically nothing but a numerical solver, right? So so from the neural network point of view, the conventional numerical solver is one special instance of the neural network. Just all these parameters are determined by human knowledge, right? So we don't need to learn; those are determined by the PDE. We know numerical schemes that we developed in the past decades and installed instead of from training data. However, as I mentioned before, like the true governing equation often partial null, and or in some cases even the null. We know the complete equations. Because the conventional numerical scheme can lead to a solver to be computationally very expensive or sometimes very unstable. So some part of the equations, for example, are very challenging to solve. Any of those scenarios can be described as this, we have the governing equations, right? Well, the some portion of it, like the K is null, some portion of it, like U is unknown, and coupling between those, between them could also be an unknown nonlinear functional or operators. Now we can leverage this vague physics to redesign this recurrent network unit and to form a PD integrated conv-LSTM for the spatial temporal predictions. And for example, we can directly encode the PD operators such as convection, diffusion, the pressure gradient in the partial null like a governing equation as a part of the neural architecture based on the relationship as I just discussed. Essentially, we built a hybrid conv-LSTM with fixed and both fixed and trainable parts. And the entire model is fully differentiable, allowing a holistic model training. So this still can be viewed as a neural network, trained like a neural networks. And so this can be viewed as an ML enhanced solver, but it's way beyond a solver since it has a strong flexibility. So we can build using like advanced deep learning architecture, for example, with this long short-term memories and with the attention mechanism. So many design that you can actually possible design that you can do within this framework. So this is this like a neural differentiable physics framework, and which actually provide a differentiable programming platform to allow the seamless and flexible blend of the incomplete physics component and trainable neural architecture component to form a novel like neural solver. Like I said, the design of this neural solver is very flexible. So let me show you just one of them to kind of showcase the idea. So let's build a conv-LSTM network to learn the spatial temporal dynamics of fluid flows. So we first to decide this next step, like learning unit, and for the sequence net and capturing the transition of the state between two learning steps, right? So to make the neural solver fast, the learning step delta t is much greater than typical numerical time step, 100,000 times bigger, and the learning unit is operating on a very coarse resolution. So we're actually developing a very low resolution models, which is efficient. And we have three convolutional residual blocks corresponding to convection, diffusion, and pressure gradient, and connected to like non-trainable convolutional residual blocks, which are actually determined by those PD operators. And the coupling between those components are based on like the momentum equation. So overall, it's a convolutional residual blocks informed by the Navier-Stokes equations. And to enable the high resolution prediction, super resolving conditional generative diffusion model is combined, which I'm going to discuss this later in detail in the second part of my talk. But before we move to like using this PD integrated recurrent unit to build a conv LSTM network, let's just test the merit of integrating this PDE operators by only use this learning unit and as an one-step predictors. And we can compare it with like the one-step predictor with same conv residual network structures, but everything is trainable. And to make the comparison fair, so the network structure size are exactly the same, and only difference is one is black box and one is hybrid. So we use the same flow problem as I showed before, and to do the comparison, and both models are trained over different like jet position and Reynolds number. So here I'm showing you two testing samples where the jet position and the Reynolds number are different, which are not seen during the training. So the left is a little bit like lower Reynolds number, and the right is a little bit higher, which is 10,000. And the first row of is a CFD reference, and middle is our PD integrated next step neural predictor, and last row is the pure black box baseline. So again, as you can see, the black box baseline can actually capture the dynamics at the beginning, and then it will become pretty noisy and physical, and clearly showing the series, the error accumulations. And this issue become more serious for the high Reynolds number case, as you can see. However, this PD integrated models on the contrary are almost like identical to the reference, even after a long-term model rollout. So this figure is showing you the error propagation over the model rollout steps, and the model is evaluated over many different Reynolds number and different jet position. That's why you see the scattering, because for some testing scenarios, they have higher error, some have lower. So from the error propagation figures, we find that the black box baseline, this orange, they will like basically dominant by the arrows, especially after the extrapolations. Well, our PD integrated one has almost like a barely see the error accumulations. And moreover, you can see the black box baseline has very large scattering over different testing cases, indicating a poor robustness. Well, our models is relatively more robust as the error scattering remains very low. So the comparison of the next step neural predictor shows the merit of integrating the governing PDEs and the architecture informed by the governing equations and to design this recurrent learning unit. And then we can use this recurrent unit and to form a sequence model. So like based on this PD integrated learning unit. For example, we can first formulate this recurrent neural networks, and then we can introduce the trainable hidden state to learn the long short-term memories, and which lead to a conv LSTM networks. So compared to the black box LSTM, the governing PDEs of the fluid flows actually embedded, blended, as I show like conceptually in this yellow box. So we can make this model to be sequence to sequence, and the loss can be defined on this rollout trajectory instead of doing like the next step teacher forcing training. So this requires a gradient that can be back propagated over the entire neural solver, including like all this, of course, neural networks and also like the the solver component. So the entire model is building using the differentiable programming, and we use the JAX, and we also use PyTorch. So here we use the JAX to enable the differentiable programming. So we can use this PD integrated convex TM network to learn and predict the 2D force, the homogeneous isotropic turbulence, namely the common growth flows. So the ground truth is generated using the DNS on the very fine mesh 2048 cube square. And we want to build a very efficient data-driven reduced order models operating in a very coarse spatial temporal resolutions, like 60 by 64, which is 32 times downscaled in each dimensions. And the time step is the 32 times of the numerical steps. But the training range is from 0 to 800 learning steps. And we test the model. First, we test the model to do the forecast, like time forecast from 800 to 1600. And the second column is a PD integrated convex TM. The third column is a black box convex TM. As you can see, both model can forecast in time, and the prediction are reasonably well. And if you compare the two data-driven models, or the black box model is slightly less accurate because you can see more noise in the forecasting regions. In comparison, like the middle one is agree with the reference very well, even at a very last step after 100, like 1600 model rollout steps. So in this case, the current equation is actually no, which is a Navier-Stokes. And you may wonder, what if I just rely on the physics without neural network component? What will happen? So the last column showing you the result of purely like a Navier-Stokes solver, even with the SGS model, because the mesh is too coarse. So the prediction has large discriminants compared to the reference, indicating that this purely using the current equation won't work in such a coarse spatial temporal resolutions. And this actually can be viewed as a traditional LES, but on a very coarse spatial temporal resolutions. Lastly, I'm showing you the error propagation plot for those three models. So we just look at these two data-driven models. The green line shows the error propagation for the black box convex TM, and the error is climbing up quickly, and also we see the large scattering, which is consistent to the previous case. And with the blue line, we can see the errors. Error accumulation issues can be significantly mitigated by integrating the like convection diffusion, those terms into the neural network architectures. So in the previous slides, the model is tested on to forecasting time, but it actually start rollout from the initial condition, which is used for training. So here we make the testing more challenging, and now we test the model to start from a randomly generated initial conditions, okay, which has not been seen during training. And then the models this time we let them to roll out for a much longer range, like 3,200 learning steps, corresponding to 51,000 numeric steps. So given the randomly generated like new initial conditions, you can see now the pure black box baseline completely fail because the predicted flow patterns are significantly deviate from the reference, even in the second row. And it becomes completely different for the longer term, like rollout, for the longer rollout lengths. Well, in contrast, so this PD integrated model can actually capture the dynamics even after like 3,200 rollout steps. Again, like pure LES solvers, it fails at this resolution because most of the flow features has been damped out. So as shown in this error propagation figures, the difference between the PD integrated convex TM and its black box counterpart is much more significant, showing like a much better generalizability and robustness in this like more like testing scenarios. So same framework can be used to design a differentiable hybrid neural solver for the fluid structure interacting dynamics. Again, we built this physics integrate convex TM network to emulate the spatial temporal FSI phenomena. In contrast to the pure black box convex TM, so we encode the FSI PDEs into the recurrent unit at the fixed convolutions, and interaction between fluid and structure are actually enforced using the immerse boundary method. The entire neural solver is fully vectorized, fully differentiable, and which is implement JAX, so it can leverage the GPU computing and can be trained as a neural network. So we showcased the model using two classic FSI problem. One's vortex-induced vibration, and others flow over flexible beams. I don't want to spend too much time to go over this again, but I just want to quickly to show you that similar behavior. As you can see, the error accumulation and the robustness for the black box models and can be significantly improved, and for using this hybrid learning structures, and also here I also want to see people may think conceptually the ML is kind of serving as a correction term or closure model. So what if I separately train a neural network to learn the discrepancy from the data and then embed it back to the PDE solver to correct it? And I call this as a weakly coupled neural PDE solver. As you can see, it is not stable at so the last column, it will quickly blow up. So the stability issue of this weakly coupled approach has been also reported in data-driven turbulence closure, turbulence modeling community as well. And moreover, if we loosely couple the solver and neural network, the flexibility is so limited, since the solver has to follow all the numerical rules and it cannot be formulated as the LSTM, right? So here I would like to emphasize this neural differential model is not simply to embed a neural network into a traditional numerical solver. It's completely we're developing a new neural networks that beyond the solver. So here I'm showing you the model can even be tested on with the different spring stiffness for this VIV case. So this time this spring stiffness has not been seen during training. So if we just do the purely data-driven black box model, it will completely fail because it cannot generalize to out of the training conditions. But you can see this approach, the second column, still very accurately capture the dynamics and agree with the reference very well. And so in this case, you can see at the beginning, the error is going up, and also for the structure dynamics is simply diverge. So for the second case, basically deliver a similar message, and I'm gonna, for the sake of time, I'm gonna skip it. And the computational cost, of course, is case dependent. If we set a cost of OpenFOAM for the high fidelity simulation on CPUs as a baseline, our fully vectorized solver on GPU without neural network can already be very fast. For the 2D VIV case, it has 7 times speed up. Well, with the neural network component, both data-driven models, matter black box or PD integrated, the speed up is over 50 times. And for turbulence case, since the DS is more costly, so speed up is more significant. Well, the training of those models is typically comparable to the conducting a single high fidelity simulations in terms of wartime. However, once the model is trained, and we can enjoy the fast speed up for performing new simulations, for example, with random generated initial conditions, different modeling parameters. So as you can see, this neural differential model framework allows us to blend the physics with the deep learning to build a novel hybrid neural models. And there are much more interesting design beyond what I've just showed. So if we have sufficient training data but very limited knowledge, and this framework turns to be the advanced deep learning frameworks, since you can use all the like advanced deep learning architectures and component. If we move to the other end where we have no data, so the neural network has to be completely determined by the physics. So now the neural differential model becomes a traditional MARC solver. However, the solver are implemented in a deep learning manner, means like they are fully differentiable and they are fully vectorized, so they can leverage GPU computing, which also significantly advanced the field of scientific computing and modeling. So for example, we have developed a couple of solvers like the GPU accelerated differentiable CFD and FSI solvers in JAX, and we call it the deep flow FSI, which is fully vectorized and fully differentiable, and it's very fast on GPUs. Like a DS simulation for turbulent channel flows with 8 million mesh cells, which is going to take about 60 hours using OpenFlow on 32 CPUs, of course, for one flow through time. But with our JAX solver, the JAX differentiable solver, it only needs 2 hours, less than 2 hours on one A6000 GPUs. And since it's fully differentiable, the solver can be easily do the forward and inverse problem, since it can be trained like neural networks, right? So the gradient can be propagated to anywhere within the solver. So for example, if the unknown physical parameters such as stiffness in the VIV case, it can be inferred using the gradient-based optimization. So by default, it has hadron capabilities. So using the differentiable neural paradigm, we're working on like different scientific problems, and each of them has its own special features and unique challenges. And for example, we developed a JAX-based GPU accelerated differentiable solver for the Fano-Boltzmann transport equations, which are high-dimensional PDEs and for the nanoscale thermal transport. So leveraging tensor computing, and we can demonstrate massive scalabilities. And we're also working on modeling, different manufacturing process where the data are limited and the physics are not fully understood. Since today the time is a limit, I'm going to spend the last maybe 10 minutes on focus on turbulence, which we know is a very challenging system and also consistent to the result what I have showed so far. So to obtain like the spatial temporal instantaneous turbulent flows requires additive resolving simulation. Like you have to do the DS, LES, which are extremely expensive, right? So many people have tried to emulate the spatial temporal behaviors, turbulent behaviors using deep learning. So for example, Camming developed this next step, CNN autoencoder to autoregressively emulate the spatial temporal turbulence for the inflow generations. And this model can be extended to like using more advanced sequence model like transformers. And our groups also like developed the graph-based transformer and to enable like the turbulence simulation on the unstructured grids. And like in the previous slides, I've shown you like this PD integrated conv LSTM to predict the homogeneous isotropic turbulence. So conceptually, all this model can be summarized as a following structure. So you have a type of like CN or GN or even POD-based autoencoder to encode a high-dimensional flow into latent space. And then you kind of use the sequence network to learn the latent dynamics in an autoregressive manner. So the model I formulate in this deterministic manner, and the training is basically to minimize the mismatch and between like with the DS instantaneous flow labels. So the model is formulated in the deterministic manners and trained to minimize the mismatch with DS label. Therefore, we are trying to learn the deterministic transition from the DS instantaneous flow data and then extrapolate kind of in time. However, we know the turbulent flow is inherently stochastic. One DS trajectory represents just one realization. And there are many possible realizations from same stochastic process that follow the same turbulence statistics, right? So a deterministic model can only at best to reproduce one particular realizations and cannot generalize to different, cannot like to generate other like different realizations under the same probability distributions. And also like because the chaotic nature of the turbulent flows, and it actually poses a significant challenge for this autoregressive model training and predictions. Well, alternatively, you may think, why not just use match some statistics of the DNS data instead of using the instantaneous flow to train a model, such as like the mean or Reynolds stresses. However, just having the model to learn a few statistics cannot guarantee you're gonna learn the same or like physical coherent flow structures. For example, even the two flows have the same mean flow profiles, instantaneous coherent structure can be entirely different. So ideally, we want to understand the probability distribution of the turbulence system. However, this is like the flow is a 4D spatial temporal stochastic process with extremely high dimensions. Think about the dimension could be like the number of time step times the number of grid points, often reach up to like 10 to 4 times 10 to 7. So to determine this probability density landscape is infeasible. Well, thanks to the recent advances in generative AI, which is a class of the unsupervised learning approach, it provides a way to implicitly extract the distribution from the observed realizations, allowing the generation of new samples that follow the same probability distributions. So in the recent years, our group has developed the generative AI-based models for the spatial temporal instantaneous turbulence generations. Just show you like some example. In one of our early work, this is done by my student Looney, who is currently also in the Livermore National Lab. So he used the normalizing flow coupled with the graph encoded transformer to learn the and generate the spatial temporal turbulent flows. And normalizing flow transformed a simple distribution into a complex one through a series of invertible transformations, allowing us to learn the complex PDF of the flow at each time step. So using this, we can generate many different realizations of the separated flows, and which each individual, like instantaneous flow field, are differing from others. However, the statistics of these flows agree with the LES reference. And we also can plot a single point velocity PDF at different locations. And so basically the PDF represented by the red line match the LES, the black dashed line, reasonably well, showing it can capture the stochastic behaviors of the flow system. However, the no issue of this normalizing flow is the scalability and make it a challenge to apply to the very large scale real world through 3D or 4D turbulence. And later we develop this spatial temporal generative model using the probabilistic diffusion based techniques, which has been very successful in the computer vision and AGI community. So like those generator, like Sora, they are based on the score matching model, this type of score matching model. The concept is very simple. So we transform the samples from a node distribution, like a Gaussian, and to the one from arbitrary target distributions through a diffusion process. So after training, we can basically generate the white noise. This white noise field is sampled and then gradually denoised using this learned reverse transition kernel, eventually form a physical field. So our model can directly handle the spatial temporal data with 3D convolutions and enable generating short spatial temporal flow samples. And this work has been published in the CMME, but the problem is in the memory footprint, because it's actually a bottleneck. You cannot really generate very large scale, like DNS level turbulence. So recently we developed this conditional neural field, a latent diffusion model to achieve the same goal, but in a more scalable manners. So the concept is we use the conditional neural field or neural implicit representations and for dimension reductions and encode a high dimensional flow field into the low dimensional latent space. And in contrast to the CN or GN autoencoders, this neural field offer the higher compression ratios and it's mesh independent, so you can handle any arbitrary geometries with unstructured meshes. And within the latent space, and we do the diffusion, and to enable the enabling the generation of the latent state, and which can be then decoded back to the spatial temporal, like physical space, and use the conditional field again. And this allow us to generate a very vivid instantaneous turbulent realizations, which are different from each other, but they look similar to the DNS. Although this instantaneous flow realization are different from each other, and you can see the statistics of this generated spatial temporal flow samples are exactly agree with the DNS. Say like the mean flow, turbulence fluctuations, and 2-point correlations. And to further test the model, so we can use the generative the flows and to fit in another like a downstream additive resolving simulations. So if the generative flow of structures is physical and it's going to the downstream turbulence simulations, there's no decay. Otherwise, the turbulence will decay. So we compare our models with the DNS precursor, which is like a reference, and also the one of the state-of-art deep learning-based synthetic inflow generators. And you can clearly see that their models, the turbulence will decay, but for ours, it actually remain this the same similar turbulence intensity as the DNS reference. So I'm going to skip those quantitative and show you like a couple more results in 2 minutes. So we can now handle like more challenging case, like flow separations with the irregular geometries where the CN doesn't work. And as you can see here, our confu can generate very diverse spatial temporal flow realizations. And you barely can see the difference of those, which is DNS, which is generated. So the first one is DNS, the other 3 are generated samples. And although the instantaneous flow of each samples are different from each other, their turbulence statistics such as mean and Reynolds stresses, TK are the same. And this is another more challenging flows involves the turbulent boundary layers and with regular roughness elements and showing this 4D spatial temporal generations. Again, you can see the generated spatial temporal turbulence are pretty similar to the DNS and also have the correct statistics. So I'm going to skip the computational cost, and if you're interested, I can talk about. But here I just want to highlight it's to generate this compared to simulate this, we're going to gain a significant speed up. And I want to use 2 slides to wrap up this talk. Is I've shown you like our confu can, once it's trained, it can generate diverse spatial temporal realizations, and which are different from each other. However, the most exciting part of this model is the conditional generation, meaning give us specific conditions, the trained model can generate that particular realization corresponding to the condition that we provide. So here are some examples of the conditions. For example, if I put a few sensors in this flow and to measure the instantaneous velocity at sparse locations, and then our confu models can immediately reconstruct the full field instantaneous flows in the spatial temporal manners. And or if we can possibly have the low resolution scans of the flows as conditions, this is quite typical in the cardiovascular applications, like people using the flow MRA and get some low resolution data, and then we can generate high resolution spatial temporal flows and that particular realizations. Another interesting scenario is we do the low fidelity simulation, such as URANS, which is super fast, and we can conditionally generate those turbulent structures and make it like a high resolution LES like result. All of this can be done using our like a Bayesian posterior sampling of our trained diffusion models without the need of retraining. So meaning our unconditional trained confu models can be used to generate those the realizations corresponding to the condition you provide in the 0 shot. So let me show you the example. Remember, like this separated flows, and it was within this channel with the periodic hills, right? So if we this time we put a few like sensors in the several sparse locations and to measure the instantaneous velocity only on the sparse locations. And this time you can see those all the generative samples, the spatial temporal samples, looks exactly the same as the flow that we are observing. So this is very exciting because we can basically reconstruct the spatial temporal flows and the instantaneous flows and using this approach. And similarly, remember previously the generative sample, they are very diverse. They are different realization, but if we put the sensors in the flows and for this 4D generation, and you can see with only very sparse sensors, and we can reconstruct the flows and even the instantaneous flows, and looks pretty similar to the flow that we are observing, we're measuring. So a little bit like parametric study, if we have just one sensor, and you can see this time all the generative samples, they kind of scattered, right? So because the condition information is so limited, but we increase the number of sensors and all the generated scattered samples, they kind of converge into the particular realizations that you are observing. And even with noise, it's pretty robust. And this is another example of this super resolution generations. Similarly, we can condition on a different low resolution, even this 4 pixel. So we still have this accurate statistics. But if we have a more informative low resolution, so you can see the generally high resolution, not only the statistic, but the realization, the instantaneous flow, they're almost the same. All right, so I think I'm going to stop here, and I'm happy to take any questions.
Well, thank you so much for the wonderful talk, Jian-sun. Let's have a Q&A sessions. Okay, we have 3 or 4 questions in the chat. The first one is from Vedant. He's asking, are your JAX solvers available on GitHub?
We haven't so yeah, it's gonna be available, but we haven't so we're working on the manuscript. So once we get it out, we will make it open source.
Good.
Yeah.
Thank you. The second question is by David. Could you comment on the energy cost of your training plus inference of your neural models versus running an equivalent CFD simulation?
Yeah, so I think yeah, let me pull up that slides. So like I mentioned, the training, so it's actually depend on what cases are talking about. Overall, the training cost, for example, for this FSI case, is comparable to conducting a single FSI simulation. So so basically the inference speed up is like this. So you can imagine you are training models, and if you just only use it once, and that's going to be this kind of a slightly have higher overhead if you just run this once. But if your training model is going to do the inference, give a different initial condition, different material properties, and for many times, okay, because of this speed up, and that will kind of you will gain a lot of saving for the computational costs, right? So it's really about the testing scenario. So, but here I'm just showing you the training of the models is for these 2 examples is kind of comparable to doing one high fidelity simulation.
Okay, so what you're saying here is you didn't include the cost of generating the data in the training as a training cost, but even though you do that,
right. So yeah, that's a good question. I've got to mention that. So for the FSI case, I just generate 2 data set because it's actually we have a lot of physics here. So you can think this hybrid model is not completely black box. That is why we test on a different a material property like the spring stiffness. It actually worked because we have those physical component there in the model. So yeah, we only have a very limited training data in that sense. It's not completely like a black box. That's why like when we do the testing or it's like given different Reynolds number, different material property, the data-driven models completely fail. But if you include a lot of training data, like in the parameter space, I believe the black box models can be improved as well. It's just that those data are so limited.
Yeah. Okay. Next question is by Sepper. He's saying, thank you for the great presentations. Have you applied your method to any examples involving 4D spatial temporal problems with known physics?
Yeah, so 4D, so currently we are doing a lot of my like applications are turbulent flow. Those are like 4D, right? So spatial temporal, and it's a 3D. So we are working on like a couple this neural software and with the generative model. So here like those this cases those are like 4D, right? But I haven't like really show you the coupling of so what we are doing. Actually, I can show you the slides. So it's kind of this is something that we already put it on the archive, but we are doing like the 4D version of this. So basically, we have the physics informed like the neural solvers and to do like the low resolution, which capture like the geometry dependent flow features, and because that is very difficult to learn, you need a lot of data and to generalize, right? So that is actually from this hybrid solver, which just has some physics, and we also have like a conditional generative models to generate those high resolution, small scale, high wave number, high frequency features, and on conditional on the low resolution like flow solver output. So eventually we can get this very high resolution predictions and with a very low cost. So here is the energy spectrum, as you can see, like the full like a spectrum, like this black dash line. This is a DES. If we only do like I didn't put LES, so LES is going to be like stop at certain wave number because you didn't resolve it, and also you have some discriminancy because the LES is because of a closure model and also like a coarse mesh, right? But with this part, and we can make this part accurate, but you still like stop here. But with the conditional generations, and we actually can recover the and almost the entire spectrum like this red light. If you just simply do like the super resolution, like bicubic, the feature going to be completely wrong. I'm just here showing you like the reference. Yes, back to the question, we are kind of like doing this on the 4D turbulence boundary layers, and we also generate a very high resolution DNS database for the turbulent boundary layers, and with different pressure gradient and with different Reynolds numbers, and we actually develop models and on that.
Cool.
Yeah.
Cool. So related questions from me would be there are many PDEs which is even more than 4D when you do the spatial temporal, like the velocity equations, it could be 60 plus times, so 7D. And then if you go to particle transport equations, it can go like all the angles, and it
Right.
can be higher and higher.
So
if your method can be
yeah.
extended to those higher.
Yeah, sure, no problem.
PDEs.
So actually, we have a similar problem. Like I mentioned here, we have another solver, and I'm going to submit a paper like probably next week. So this is solving the Phonon-Boltzmann transport equation. So it is a high-dimensional PD. It's not just about space and time. We also have the frequency band angles of the phonons, and so it's actually like it could go up like to 8 or 10 dimensions. So those are like high dimensional PDEs, and we developed a JAX differentiable solver for that, and the solver is also like fully like vectorized, and we also kind of adding like tensor computing component to that solver. But now the solver is very scalable, and we can do like the steady state and the transient phonon transport, phonon Boltzmann transport simulations on the transistor. So the very regular. Oh, by the way, this solver is also like unstructured, so we can handle a very like complex geometries. So actually simulate the heat transfer in the complex transistor for the computer chips and study the nanoscale heat transfer. That is a high dimensional PDE.
All right, super nice, very nice. Okay, next question is by Jun Gang. He said, "Thanks for the presentation, Dr. Wang. Is your model relies on adjacent data pairs to train XT and XT plus 1? In that case, wouldn't the error accumulate when doing recursive predictions? Did you consider longer data pairs to train?"
Yeah, actually, so what I'm showing you is like this next step. We here when I'm showing you like when I try to see like why this like was this like PD informed structure compared to everything is trainable, and I just want to show you like using this approach, and even we build a next step models, and we have a much better performance in terms of the error accumulation. So we can mitigate the error accumulation significantly compared to the black box. You are right. So if you just like do the teacher forcing black box, and you have a significant error accumulations, but even like we formulate the same thing like next step models, this explicit time stepping, right? So the error accumulation is there is some error accumulation, but it's very minor. But this is not the optimal form of the model, so you can use that to construct like the more like advanced the sequence model, like the here I'm showing you the ConvSTM. That so actually we're using the entire trajectory, so not entire but longer trajectory to do this sequence to sequence training instead of teacher forcing. So that is why we have to make this entire things to be differentiable, because if your loss is based on not just the one day like t to t plus 1, it's actually t, t1, t3, t4. So you have to make sure that your gradient can be propagated to through this recurrent structure, right? So every component, they have to be differentiable, so then you can do the back propagations. So that is why it's very important for this differentiable programming, using the differentiable programming.
Okay.
Answer the question?
All right. Next question is Fei Zhao. He's asking, generative models are expensive to train and require lots of data. Any idea on incorporating physics in your generative model?
Yes, that's a good question. So basically, the generative model is expensive to train, and actually we found that so try to avoid memorizations, and there's a couple of techniques, hierarchical training, so on the low resolution, but I don't want to talk about that. But so that cost can be reduced, and also if we are not training a general purpose the generative model. So like a Sora, they want to learn everything, and we just generate the videos for the word. That's going to be very expensive. But if you just focus on like one particular problem, the subset of problems, so the required training data is not that as much as what they need, like for the general purpose generative model. But still, we need a lot of data. So that's why at the very last slides, I just show you like we're trying to kind of leverage like this physics, hybrid physics neural solvers and as a base. And we use that to kind of simulate large scale flow structures, and on top of it, we generate small scale. So the reason is that the small scale flow structures, especially when the flow structures like turbulence structures go to like common growth, we know it's universal across all the different flows. So that means you have a lot of data. So everybody generate them like high fidelity simulations and for different cases. And if we only look at the small scale, so those are the data is huge. And but the problem is we want to couple it with like a more physics informed or physics integrated like solver that can roughly accurately capture like the large scale structures, which is more like geometry and boundary condition dependent. And so that is the what we are doing, and maybe the next step we are working on.
All right. Next question is by Rick. He said, nice talk. Can you comment on the training requirements, data time, for the last presented results like stochastic modeling of transient turbulence?
So actually, we are also learning this. So like the model. So the last model we so I think here I have shown like two different models. One is orange one, like the video diffusion, and the training for that is very expensive, a couple of days, and because you know the memory issues, and you directly deal with like 3D convolutions. You know, the best GPU can fit data like 128 cube, and you cannot even like do the convolutions on data larger than that. So once we have this decoupled diffusion, so sorry, we have this latent diffusion, the training cost can be significantly reduced because we are, instead of like generating the 3D flows, we're only generate the latent vectors, and because it's spatial temporal, so you can think of this latent images, and previously we kind of overtrained the models, so we found it has memorization issues. So you can continue to train like a diffusion model for like days or even weeks, and eventually it's gonna if you continue to train, it's gonna memorize things. So memorize your train data. So, and later we kind of reduced the training and put a constraint. So to kind of enforce the models, basically to reduce the memorizations, and the training is relatively fast. So for I think for the like the turbulent channel flows, this can be done in like 10 hours, and so I don't there's not an exact number in my hand, but I can check with my student, but that is a rough like training time for now.
Okay, well, thank you. Next question is by Hongyu. Great talk. Did you work on high-dimensional input space, for example, heterogeneous material properties for fluid mechanics, etc.?
So
Like the distributed input parameter space, like in space, yeah. So for example, topology optimizations, you use the density-based method. Every single element has the input parameter, and it's distributed in the space. And in the geoscience, you know, all the materials is unknowns, and each element you have to define, you know.
yeah,
So it naturally becomes high dimensional. Yeah.
yeah. If so, yeah, we have done a lot for like a field inversion. So I think yeah, one of my students actually here, Deepak, so he is doing like more like the solid mechanics. And like a field inversion. So it's entire field, like each element you have a different property, right? So if I don't know, like the intrinsic dimension is actually if it's a mesh dimension, then the field is like a white noise. So essentially, this intrinsic dimension is lower than the mesh dimension, right? If the field is continuous, so definitely that can be, the dimension can be reduced. Yes, we have been working on that as well. So for example, like we one of our project, we kind of model the manufacturing process of the carbon-carbon composite, and within the oven, like you blow the gas and natural gas, there will chemical reaction, and will deposit the carbons and densify the porous medium, which is the preform. And so we built the carbon-carbon composite, and we're trying to model like the physical process involves like the diffusion, reaction, deposition, and currently we haven't considered the gas convection, but that can be considered if you have like a high-speed flow balloon, like blowing this within this oven. So for that problem, so the porosity is the spatial temporal field, and there are some many like spatial temporal field that we kind of model the basically the operator between those. And we also have some physics, PDEs, to describe the operator. So it's actually another like hybrid models. I haven't particularly done like anything with topology optimizations, like using the FEM. But I think yeah, we can discuss if you're interested.
Okay, next question is by Sepper. Could you compare the data requirements of your methods to neural operator approaches such as CNO? What does C
FNO?
stands for?
Is that FNO?
Probably FNO. Okay.
Actually, I didn't put. Actually, we did some comparison with the neural operators. Let me see if I have that slides. So wait a minute. So yeah, this is a comparison of this is like we actually, because as I mentioned, we're using like we're using the neural network to learn the operator. So from t to t+1, this is like operator. So it's essentially it's an operator, right? So basically, we use the same amount of training data. Everything is the same. Actually, this is a collaborative work with Lulu. So some of you know, like he is the first author of the one of the DeepNet. And we actually we send the data to them, and they do the DeepNet. They have like a variant of DeepNet and DeepNet large. And we also test on the FNO, and it was the same data set. So basically, as you can see, like with this PD informations, actually it does help. So here what I'm showing you is the arrow on the testing. Okay, sorry, both training and testing over the model rollout steps. And this dashed line is our in the training scenarios, and the solid line is in the testing scenarios. And you can see it pretty consistent for our models, and it shows a good generalizability. But if you see like for DeepNet, and they have higher arrows, kind of like no matter training and testing. So for the FNO, for a neural operators, so they have very good fitting capabilities. You can see like this training, they actually can fit the data very well, even like sometimes lower than what we have here. But if you use this train and on testing scenarios, then the error goes up. So it shows that they have kind of overfitting. So all of those models, if you formulate this as like next step, you are learning the operators to define the transition, right? So all of them will have the error accumulation. Some of them have a very serious error accumulation. Some does not. It's kind of flat. But overall, you can see it is a little better. So we also not just compare the error, but also like the memory footprint and inference cost, right? So for all this neural operators, and you can see the memory footprint and our approach. And here is a PD preserved network, so it's weird PPN. But anyway, this is ours. So it's kind of comparable to all the other models, and also the inference cost is also kind of comparable to the other models. Here the pin, because we need a very large network to capture the dynamics. So that's why the inference cost of this is large, because the network is large, right? So for the other models, it's actually comparable. Okay.
All right. Awesome. Okay. I don't see any more questions in the chat room, but I would like to ask one questions. So I'm pretty fascinated by bringing the physics operator, the differential operator in the architecture of the neural network. Okay. So the time derivative terms, the neural ODE concept, like the recursive neural net, makes sense. And the convolutional, it's basically, the diffusion operator makes sense, totally makes sense. How about the convection terms, like the gradient dot, right? That one, but has a direction in it. So usually, up in the scheme, it take account of the where the flow is coming and go.
Mm-hmm.
How do you handle that within to the architecture, neural architecture? Do you even handle that in special manner or?
So I think you can basically encode like the convection the same way like you do it in the solver. So it can be upwind. So it's there's no problem. So you can still handle that. Or you believe that you want this model to be more data driven instead of like more like numerical solvers. And those like numerical scheme can also be trainable. So that's a why it's very flexible. So for example, what I have shown like we can basically like have the convection exactly leverage the existing like upwind schemes that we used in the CFE solver, right? So I showed in the one of the slides. So we can completely like rely on the PD. So we actually implement all the different numerical schemes, and our solver is not just a simple like numerical solver. It actually have those numerical scheme like the different time stepping implicit, explicit, and we also have energy preserving like spatial schemes. And overall, it's a finite volume based, but we can leverage the advanced numerical schemes and to handle those terms. But sometimes, when we think, okay, probably we can learn a better scheme from data. So that is also possible. You can just make those coefficient. You can so for example, we have Vino, but we have Tino Vito, those schemes, and the coefficient can be determined using our traditional like numeric Vino scheme, but it can also be kind of
data driven.
data. Yeah. So that is flexible. Yeah.
Okay, cool. Okay, Sepper asked another question in the chat. That is a very great paper. Is the code for the paper available anywhere? I think you answered the questions before.
Which paper you're talking about?
Sepper, would you elaborate on that? Multi-resolution partial differential equation preserve the learning framework for spatial temporal dynamics.
I think that is the code is also published, also open source.
Okay.
You can find it in our group's GitHub. I think there's a link in the paper as well.
Okay, sounds good. Any other questions, guys? It has been a wonderful the presentation and wonderful Q&A sessions.
Yeah, I really enjoy it.
If there's no more questions, we can just thank Luning is sending the heart to you.
Yeah, thank you, Luni.
All right, thank you so much for the Jian-Sun. It was a wonderful talk, and we learned a lot. And I mean, personally, I'm very fascinated by that architecture concept. So probably I will contact you separately, and I'm sure other people is going to do the same things.
Thank you. Yeah, I'm happy to continue discuss with you, and let's see if we can initialize some collaborations.
Exactly. All right. Thank you so much.
Thank you, everybody. Have a nice weekend.
Thank you. Luning, no, not Luning, the Jian